Hello everyone, my name is Tasmay Togarkar. I would like to welcome you all to this video lecture on music recognition using audio fingerprinting. So this video is a part of the digital signal processing course that I'm currently studying in my fourth semester BTech at NITK Surathkal. So many a times it happens in our day-to-day lives that a song is being played in our surroundings and we really like the sound of it. But we don't really know the name of that song, what is it called, who is the artist behind it. So what we do is we would just search the lyrics on Google and we would get the song's name. But it is not possible every time, right? What if you don't catch the lyrics properly, or what if the song is of another language that you don't know, or what if it's just plain music, there's no vocals in the song. So in that case, you will have to rely on a software such as Shazam. Okay, so now I'll quickly demonstrate what I'm talking about by giving you a practical example. So I'll play a song which is called Invincible by Def KEV. So this is Shazam. Okay. So as you could see, the software correctly guessed the song's name, which is Invincible. So the main objective of this video is to uncover the technology behind this, how Shazam basically uses the technique of audio fingerprinting to recognize the music. So now I'll introduce you to what I'll be discussing in this video lecture. So let us say you are in a club where a lot of people are there, they are talking, they are dancing, they are singing their own song, someone is coughing. And despite all these noises, you would like to instantly identify which song is being played in the background. So this is the main problem statement, or you can say the challenge, that we need to recognize audio in chaos. So one should understand that this is not an easy digital signal processing problem because of three major reasons. The first one is low signal to noise ratio. So what it means is that the core data, the core audio is less as compared to the noise which is in the surroundings. Second is distortion challenges. So what if a person is capturing the audio from cheap quality microphone, which would itself introduce some significant distortion. So that's a challenge. And the third challenge is uh, so in the database there'll be 50 more than 50 million unique songs. So out of all those 15 million unique songs, you need to efficiently search and match that one particular song, which will give you the correct match. Okay. So the solution to these three problems is audio fingerprinting. What it means is that uh, we'll basically be making a fingerprint which is basically you can say an identity card of the audio sample which we'll be taking. So instead of matching bulky, noisy raw audio, we extract a compact, unique digest. So that digest is basically nothing but the fingerprint or the ID card of that song. So we need to design a system which is storage friendly, it is robust to noise, and it also gives me the output very quickly. So this process is a four-step pipeline. Means there are four steps in this audio fingerprinting processing. So the first step is audio fetch. We'll be fetching the audio from the microphone. Second is we'll be taking that audio signal and we'll be performing short time Fourier transform on that signal. The third one is we'll be taking constellation mapping. I'll be explaining all these things in detail. And the fourth and the last step is hashing and indexing. So, as I already told, the main idea of this video is to uncover the technology behind audio fingerprinting, and we'll be looking through the core digital signal techniques that enable this audio fingerprinting. So, in the next scene, I'll be discussing the core mathematics of audio fingerprinting. Okay, so now I'll be discussing the mathematics of audio fingerprinting. So the main mathematical tool which we'll be using for audio fingerprinting is the discrete Fourier transform or the DFT. So the DFT is basically a discrete frequency domain representation of a discrete time signal. So let us say you have a discrete time signal x of n. You take the discrete Fourier transform DFT, and it will give you a discrete frequency domain representation x, capital X of k. So this k is basically a representation of the frequency, but it's a discrete form of frequency. Okay. So it should be noted that discrete Fourier transform is the main mathematical tool, whereas the fast Fourier transform or FFT is just an algorithm. So algorithm to compute the discrete Fourier transform quickly. So you have a discrete Fourier transform, and you calculate, you compute the discrete Fourier transform very quickly. Because this discrete Fourier transform would be computed by a software, it needs to be very efficient, right? You need to calculate it very quickly. So that algorithm is given by the fast Fourier transform or FFT. But to its core, both of them are same. This is just an algorithm, whereas this is the tool. Okay. So now this discrete Fourier transform being the main tool, we'll be using this to convert our audio signal into a frequency domain representation. Now, we won't be, okay, I'll be using the term fast Fourier transform from now on because that's how the software will actually be computing it. But the thing is, we won't be using fast Fourier transform in our audio fingerprinting. Rather, we'll be using something known as short time Fourier transform or STFT, short time Fourier transform. Now, short time Fourier transform basically is a process of computing fast Fourier transform. Now, I'll be discussing what exactly is short time Fourier transform. But before that, I'll be taking an example of two signals and demonstrate why fast Fourier transform is not used and rather uh, a process of fast Fourier transform, which is called short time Fourier transform, is used. So consider two signals, signal A and signal B. As you can see, signal A is having low frequency in the beginning and it's gradually increasing to a high frequency till the time t naught. And the signal B is just the is just like a converse of signal A. It begins with a high frequency in the beginning and it gradually reduces to a low frequency till the time t naught. So let us say x of A. So if you can observe clearly, uh, the signal B is nothing but a reversed, time reversed form of signal A and then shifted by t naught seconds. So you can write xb of t as xa of minus t plus t naught. So you're just reversing this signal and then you are shifting it ahead by t naught and you'll be getting xb. Okay, so this thing we need to keep in mind. So now I'll be sampling this continuous signal because this is in continuous time domain. I need to sample it and convert it into a discrete time domain. So let us say x of a, xa of t, my bad. Xa of t is uh, being sampled and it's getting converted to xa of n. And similarly, you have xb of t getting sampled and getting converted to xb of n. So from this, you can write xb of n is equal to xa of minus n plus capital N. Okay, so this particular expression is the main expression. So now I'll be taking the discrete Fourier transform of xb of n and xa of n. So let us say xa of n, the Fourier transform is sorry, my bad, the discrete Fourier transform. The discrete Fourier transform of xa of n is capital X a of k, and similarly for x b of n we have xb of k. Okay. So uh, now, because xb of n is xa of minus n plus capital N, its corresponding discrete Fourier transform will be capital XA of minus k plus n. Okay, this is nothing but xb of n, xb of k. Alright. So now there's a property of discrete Fourier transform that it is periodic with period n. So since we are taking n samples, so it's periodic with period n. Okay, so I can write this, but the thing is, so you write xa of k plus n. What it means when I say the discrete Fourier transform is periodic with period n, it means that xa of k plus n will be equal to xa of k. Okay? But here I am reversing the time, so the property slightly changes to something like this: xa of minus k plus n. You are reversing the time and then shifting. That equals to xa of k, but the conjugate of it, conjugate of it. But you know what, for our discussions, this conjugate wouldn't really matter because we'll just be taking magnitude. So if we take the magnitude of it, these both are the same. So by property, I can write xa star of n means the conjugate of this xa star of k will be equal to xb of k. But as I already said, we'll just be taking the magnitude. So the magnitudes will be the same. And the magnitude of conjugate is the same as the magnitude of the original signal. That's yeah. So now the point is that these two signals are completely different signals. So this will have its own different sound. This will have its own different sound. But when we calculate the discrete time Fourier transform, sorry, discrete Fourier transform, they both are having the same DFTs. And this is not desired at all because these two are different signals, right? They cannot be having. So if we are doing signal processing, we need to distinguish between both of them. They have to have something distinct. Since we are fingerprinting it, so we are basically calculating we are finding out the fingerprint of this signal and fingerprint of this signal. What do we mean by fingerprint? It has to be distinct, right? This is same. So now we need to do something about this, and we need to carry out a process known as windowing. Okay, so we'll be doing windowing over this Fourier transform, and that process of windowing the Fourier transform, the fast Fourier transform, is known as short time Fourier transform. Okay, so I'll be explaining what short time Fourier transform is. Yeah. So let us consider a signal. Let us say a random signal like this. We have this signal. Uh, this is say x of t, and this is t. Now what I'll be doing is I'll make windows. What I mean by windows, I'll basically be chopping this signal into slices like this. I'm chopping it into slices, and these slices are overlapping. Okay, yeah. So I've made these slices which are known as windows. So each of these brackets represent a window. So I'll be naming this bracket as P1. I'll be naming this bracket as P2, P3, and so on. Okay. So now what I'll be doing is I've sliced the signal into windows, and now I'll take fast Fourier transform of each of these windows. So earlier what I was doing is I was taking the fast Fourier transform of entire signal, but now I'm chopping it into windows and I'm taking fast Fourier transform of these individual windows. Now, why to do it? Why are we chopping it into slices and calculating the FFT? Because earlier the FFT was giving me only two things. One is what frequencies are present in the signal, and second is what are the amplitudes of those frequencies. This amplitude of the frequency. So earlier FFT was answering only these two questions. But now, this HTFT, short time Fourier transform, is answering three questions. First question is the same, what are the frequencies present? The second question, which is the most important question now, is at what time these frequencies are occurring. So, at what time these frequencies are occurring? And the third question is the same, which is what is the amplitude of those frequencies? So, this time part is the crucial part now because now I'm having another dimension of information, which is at what time these particular frequencies are getting, at what time these particular frequencies are occurring in the signal. So, since we are taking this T1, T2, T3, these are giving me that information about at what time those frequencies are occurring. So, the fast Fourier transform is giving me a two-dimensional plot of frequencies and amplitude, and the short time Fourier transform is giving me a three-dimensional uh, plot. Uh, it's not really three-dimensional; it will be depicted in a two-dimensional representation only, but it will have colors. So, what we call as spectrograph. Spectrograph. Okay. So this will be having time, this will be having frequency, and it will be having different colors. So the color would be depicting the amplitude. So it will have, say, yellow color, then we'll have red color, and so on. So this is how we'll be using short time Fourier transform. So if I were to give you an analogy of what I'm talking about is, let us say you have say fruit milkshake. Okay, you have a fruit milkshake. That fruit milkshake contains 40% strawberries, 30% bananas, and say the remaining 30% is milk. Okay, just to take an example. So this is strawberries, this is bananas, and this is milk. So now, when I'm giving this composition to you, what I'm doing is I'm taking a fast Fourier transform of this milkshake. So it is telling me what is the what is the percentage, what is the composition of strawberries in this milkshake, what is the composition of bananas in this milkshake, and so on. But now, if I tell you, for some reason, let us say you need to know at what time you have put the strawberries, at what time you have put the bananas, and at what time you have to add the milk. If due to some reason you want to know that, that would be saying that would be like taking the short time Fourier transform of this milkshake. So you can think of the recipe as the short time Fourier transform, whereas the composition of the milkshake is just the fast Fourier transform. Okay, so now just to get a visual picture of what I just explained, I'll be using Jupyter Notebook, that is Python programming, to demonstrate why instead of fast Fourier transform, short time Fourier transform is used for audio fingerprinting. So as you can see, we have these two signals, signal A and signal B, which we had taken earlier. So signal A is having a low frequency initially, and it's gradually increasing to a high frequency till 4 seconds. And on the contrary, signal B is having high frequency and it's gradually reducing till 4 seconds. So now if I execute this program, I'll be getting these two plots. So these two plots are the fast Fourier transform of signal A and signal B. So as you can see, these two plots are these two plots are exactly the same, right? There's absolutely no difference between these two, and there's no way we are taking fingerprints of our signals. So in other words, if we were to give these two signals to Shazam, they would give the same match, despite these two being completely different. So that's not what we want, right? Because our audio signals are completely different, but we are getting the same match. So now, if we look at the Python program, this program will basically be finding both the fast Fourier transform and the short time Fourier transform. So if you look at this part, fs equal to 500 means the sampling frequency is 500 samples per second, and t is equal to 4, which means the signal is for is running for 4 seconds, right? So this is for that. So now if you multiply 504, which is 2000, so what it means is uh, our entire signal is getting is getting divided into 2000 samples. So that's what it means. Now these two signals are signal A and signal B. These two are standard chirp signals, and this block calculates the fast Fourier transform. And now if you look at this block, this is where we are getting our spectrogram. I'll be showing the spectrogram. So so basically, if you look at this part, n per seg equal to 256. Now what this means is we are having 2000 samples, right? So I'll be dividing those 2000 samples into chunks of 256 samples. Okay, so if you recall, I discussed about windowing, right? So I'll be dividing the entire signal into separate windows. So this is where that windowing comes. Okay, so basically, these 256 samples are being we are taking the fast Fourier transform of these 256 samples at the same time. So what we are doing is we are dividing the entire signal into 2000 samples, and we are taking chunks of 256 samples, and we are taking the fast Fourier transform of each of those chunks. So that's what it means. So if we were to calculate number of windows, or in other words, the number of chunks, we would take 2000 and divide it by 256, and it would give us 7.8, approximately 7.8. So it means we'll be having approximately 7.8 windows in our audio processing. But we should note that there will be slightly more number of windows than 7.8. The reason being the windows are overlapped. So why we are overlapping the windows? Because we don't want to lose any data. So let's say if we were not overlapping the windows, so if there was some spacing between the windows, the data which comes between those windows will be lost, and we don't want that. So that's why there'll be more than 7.8 minutes. So now I'll be showing you the spectrogram of the signals. So yeah, these two are the spectrograms of signal A and signal B. And as you can see, these two are completely different. Uh, so now over here, I'm getting information about three things: the frequency, the time, and the color, which is depicting the amplitude. So in signal A, which was initially having low frequency, and after some time it was increasing to a high frequency. So as you can see, it's gradually increasing, and for signal B, it's gradually reducing. So now we can say that we are having distinct information about signal A and signal B, and we can move further and take uh, things to the next level so that we can finally get the fingerprints of signal A and signal B, and we can match it to the reference audio. So let's move forward. So till now, what we have done is we have fetched the audio from microphone, and we have taken the short time Fourier transform of the audio. And that short time Fourier transform would give us a spectrogram. So I've taken an example of a trumpet audio signal, and this is the spectrogram of the audio signal. So now the next step is to so you would be thinking that we just need to match this spectrogram with the spectrogram of the reference audio signal, right? But that's not correct because of two major problems. Okay, so the first problem is that this spectrogram is having infinite data points. So in other words, this spectrogram will occupy a lot of space. So we can't really match every data point with the with every data point of the reference audio signal, right? And moreover, it's not really needed also because we just need to match the characteristics of the two audio signals. We just need set data points. So what we'll do is we'll just take set data points. We'll just choose these set data points known as constellations. So I'll be telling what constellations are. So we'll be choosing these constellations, and we'll just be matching these points with the reference audio signal. So this is the first problem. And the second problem, which is the most important problem, is noise. So this entire graph is also containing noise within itself. So as you can see, these lines where the graph is getting faded out, these and also these smudges, these most likely represent the uh, noise signals which are getting added to the main data signal. So, in order to solve these two problems, what we do is We basically, again, we just choose these data points. We keep choosing these data points, but just choosing the data points would solve the first problem, which is taking a large data and converting it into a small data, which is just having discrete data points. But in order to solve the second problem, which is the problem of noise, we need to answer the question, how do we choose these data points? How do we choose these dots? So the answer is very interesting. The solution is very interesting, which is in order to remove the noise, we'll just choose the points with highest amplitude. So if you look at this graph, the places where the lines are the brightest will show the points where the amplitude is the maximum. But we won't be just choosing this entire band of the graph. Rather, we'll be choosing the local maxima. So if say this is the local maxima, so we'll be choosing, let me choose another color. So if this is the local maxima, we'll be choosing this point as the data point, and if this is the data point, then we'll be just choosing this. So that's how we'll be choosing the data points. So let us take an example of this graph. So let us say this z-axis is representing the amplitude, this is the frequency, and this is the time axis. So what we'll be doing is we'll be choosing these local maximas, these points as our data points or the dots, or also known as constellation points. So we'll be choosing these points. So the thing is, there is a high probability that these data points, these maximas, will only be the main data or the main audio signal and not the noise. So there's a high probability that there's a high chance that these points are the main audio signal and not the noise. All right. This process of converting this spectrogram into these dots, the plot of a dot, is known as constellation mapping. Okay. So now I'll be showing you the actual constellation map of this spectrogram. So this is the spectrogram of the trumpet signal. So I've taken the trumpet signal from the Librosa library of Python. You can see the code over here. So this is the spectrogram I showed, and this is the corresponding constellation map. So as you can see, this constellation map is having a lot of dots over here. So these dots are nothing but the constellation points, and each of these dots will give us information about two things. So let us say this data point. So if you take this point, it is giving me the information of which frequency is being associated with that point, and secondly is when is that frequency occurring in that song. So it's giving me two things, frequency and the time. Okay, so this basically, you can say this is not exactly the fingerprint, but yes, this can be called as this is the outer layer of the fingerprint. But we still need to do something more about this constellation map, and that we'll look in the next scene. So now I'll be discussing the final two steps in our audio fingerprinting. So let us take an example of this constellation map of some audio sample. And now you would be thinking that we can just take this and then we can just compare it with the constellation maps of all the songs which we have in the database. But that's not possible. There are two problems in this. The first one is that if you were to take every dot over here and map it with all the songs, the millions of songs, it would take hours of processing time, and that's not practical. So that's the first problem. The second problem is, so I want you to understand that this constellation map is giving me the information of what all frequencies are present. That's the only thing which it is telling you. You'd be thinking that it's also telling me when those frequencies are occurring, right? But that's not quite right, because consider this point. This point is of 300 hertz and it's occurring at 2 seconds in my audio sample. So it's occurring at 2 seconds in my audio sample, but I don't know when this point is occurring in the original studio track, right? So in my recording of 10 seconds, a dot might occur at 2 seconds, but in the original studio track, that same dot might happen at say 1 minute 42 seconds. So I don't know that. So now what I mean to say is that these dots So let us say this dot. So this dot will be present at this dot will be present in millions of songs that I have in my database. Same with this dot and same with this dot. So because this is giving me only the data of what all frequencies are present, this would give me millions of matches. So I don't want that, right? So how do I solve this problem? So in order to solve this problem, let us consider this point and name it as A. A stands for anchor point, and this point is T. T stands for target point. So now somehow, if I know this relative spacing between these 2 points, so if I somehow get to know that if this point is occurring at this 300 hertz is occurring at 2 seconds, if after this 300 hertz, say at 4 seconds, if I somehow know that a 500 hertz is occurring, then I can say that this particular piece of information is something which is exclusive about this constellation map and my audio sample. So this process of taking this relative spacing is known as hashing. So we'll be making these hashes. So let's say we were to write the hash of this particular these 2 points. So it will be like FA, which is the frequency of this A point, anchor point. Then we'll write FB, which is the frequency of this FT, which will be the frequency of this target point, and delta T, which is the time spacing between these two, like after how much time this point is occurring. So, relative to this point, basically, yeah. So, now if I were to take an analogy, the constellation map was telling me that in a song, a C note was happening. C note is some frequency. So, in the constellation map is only giving me information that a C note was happening. But now this hashing is giving me information that a C note is happening, but after say 0.43 seconds, a D note is happening. So this piece of information is something which is exclusive about my audio sample, right? So now uh, I'll just keep taking these hashes. I'll be having several thousands or millions of hashes depending on the size of the sample. And now these hashes, this data set of these hashes, is what we can call our final fingerprint. So this particular data set is my final fingerprint of my audio sample. Yeah. So this is something which is exclusive. This is something which will be like an identity card of my audio sample. All right. So then in the next video, I'll be in the next scene. I'll be explaining what's the other step, the final step of audio fingerprinting. I would like to add a small detail about the hashes. So these hashes are represented as 32-bit binary integers, where 9 bits are allocated to both the anchor points and the target points, and the delta t is having 14 bits. So it is represented as 32-bit integer because uh, it fits perfectly in computer architecture, and it basically so our servers can use those 32-bit integers as direct memory addresses, and it can compare millions of hashes in just milliseconds. Yeah. So now we'll be moving to the final step of audio fingerprinting, and it is known as temporal alignment. So in this step, we'll mostly be just matching the our sample audio with the database song, and we'll be giving the result as which database song it is. So let us consider a database song which is 4 minutes long. So this database song is basically nothing but the original studio track. So and let us say that we have started recording the audio. So we have basically pushed the Shazam button when 1 minute of the song got over. So at this point, we have hit the Shazam button and we are recording the audio for 5 seconds. So now let us say that this sample audio is giving matches to this particular song of 4 minutes. And because it's just 5 seconds and Shazam has to detect the song within 1 or 2 seconds, there's a possibility that this sample audio will also be matched to other songs. So how do I know if it's this song and not the other songs? So I'll take this particular delta t. So from 0 to this particular A. So there'll be many points which will be matched to this song but I've only taken 2 points just to demonstrate. So I'll take this delta t. Let us call this t database. T database. I'll take this. I'll consider this, and then I'll take this delta t also, and let us call it t sample. So I'll calculate T database and I'll calculate the difference between T database and T sample for all the points. So for A, I'll calculate, for B, I'll calculate, and so on. I'll calculate all the points which are getting matched. And if that particular value is a constant for all those points, I'll say that this is the song which is getting matched to this sample object. So this constant is nothing but the offset. So this is the time at which I started recording the audio, the time at which I hit the Shazam button, and in this case, it's 1 minute. So basically, the idea is if you calculate the graph between T sample and T database, it should be a linear graph with 45-degree angle, 45-degree slope. So I've calculated the graph, the the graph between time in recorded sample and time in database song is coming out to be if it's coming out to be a linear graph with 45-degree slope. I can say that my sample audio is the same as the is basically a part of the original studio track, which is in my database. So there'll be the most of the points will be lying on this line, and there'll be some points which will be away from this line. So these points are mostly the noise, the noise dots which were getting anchored while carrying out the hashing process. So if so, basically the core idea is if we get this straight line, our sample audio is equal to the original studio track, and this marks the end of this video. I hope you understood the basic working of how of audio fingerprinting and how Shazam actually works. Thank you.